Hey there! If you want to study deep reinforcement learning, don't go anywhere, you're in the right place. My name is Thomas Simonini, and I'm the founder of Deep Reinforcement Learning course with Tensorflow, which is a free series of articles published on FreeCodeCamp. In this series of videos, we're going to focus on the implementation part with TensorFlow, while on the series of articles, we'll focus on the understanding of the architecture in detail. So today, we'll implement a policy gradient agent that learns to play Doom and survive in a deathmatch environment where enemies are spawned and must kill the maximum of them with a little amount of ammunition. So, it's the first time of this series that we implement a policy-based method instead of a value-based method. That's why you need to first understand what is policy gradients. To do that, you must read my article about policy gradients. The link is in the description of the video below. This will provide all that you need to understand policy gradients and the mathematics behind. Again, if not a math guy, that's not a problem. Don't be scared because every formula will be explained in the article step by step. So you're ready? Let's implement our Doom playing agent. Let's do it.
I'll give you $20 if you come and do this with me.
Interesting. 1,000.
28.
29.50.
Deal.
This is gonna be the hardest money I have ever earned.
Unless you become a hooker.
Okay, so today we'll implement a policy gradient agent that tries to survive in Doom environment by killing all monsters that are spawned in the map. So you can see here our agent playing after about 206 epoch with a batch size of 1000. And as you can see, our agent begins to understand that he must kill the enemies, but is not really rational. As you can see in the beginning of the episode, he shoots a lot here, and we don't know why. But in fact, what we must understand is that this agent needs more training because we need about 5,000 epoch and a batch size of 5,000. But I train it on my computer, so I can't make 5,000 batch size without freezing my computer. But what you can do here is that you can use my pre-trained model to train, to continue to train your model. So, as always, we begin by importing the libraries, and today we'll use what we call VisDoom. So VisDoom is an open source version of Doom, and we use that as our Doom environment. So we create our environment. Our environment is VisDoom, and we must understand how works VisDoom. So VisDoom takes two files. The first is called a configuration file that handles all the options, for instance, the size of the frame, the color of the frame, the possible actions, etc. And the second is a scenario file that generates the correct scenario. In our case, defend the center, but you can try other scenarios such as health gathering or basic, etc. So we have three possible actions: turn left, turn right, and shoot. So now let's understand our environment. So the purpose of the scenario is that our agent understands that killing monster is good, but being killed is bad. And in addition, wasting ammunition is not good either because he has a limited amount of ammunition. When he kills monster, he wins +1. When he dies, he loses 1 point. Okay? And it's inevitable that he dies because he has a limited amount of ammunition. So he can't kill all the monsters. Okay, so here we create our environment. So we create game. So we load the correct configuration, in our case defend the center, and load the correct scenario. We init the environment. And here, in fact, we generate an array that contains 3 arrays inside. Each of them is one hard-coded version of our action. So for instance, is left, right, and shoot. And then here we create our environment that returns our game, so our environment, and the possible action, which is the one hard-coded version of our actions. So now that we created our environment, we can define our preprocessing functions. As explained in the last video about DeepQN with Space Invaders, our first preprocessing function is called preprocess frame and is essential because we want to reduce the complexity of our states to reduce the computation time needed for training. So our steps, first of all, we grayscale each of our frames because colors does not add important information in our case, but we don't need to do that in VisDoom because it's already done in the configuration file. Then we crop the screen. In our case, we want to remove the roof that does not add important information. So we remove 40 pixels from up. Then we normalize the pixel values. And finally, we resize the frame. In our case, we resize by 100 by 160 pixels. So then we stack frames. So stack frames, as explained in the last video, is an important step because it will give our neural network a sense of motion. So what we do, in fact, this is how it works. So first of all, if we are in a new environment, and if we are in a new episode, we must first of all stack the same frame 4 times. Okay, as we do here. So we stack the frame. Otherwise, if we are here in the next state, what we do, we take the new frame and we stack this frame here. So we remove the oldest frame, so this frame, and we stack the new frame here. And to do that, we use DQ. That helps us to do that because DQ, when we add an element of DQ, it removes the oldest element. Okay, but here we add a new preprocessing function that we didn't have in TD learning, because remember that what we do with Q-learning and deep Q-learning, it was temporal difference learning methods. It means that we estimate the rewards at each step. But in fact, in policy gradients, I explained in the article, we are in a Monte Carlo approach. It means that we're collecting the rewards at the end of the episode and then calculating the maximum expected future reward. So we need to discount the reward at the end of the episode. So this function takes the reward, discount it, and more further is the reward, more discounted it will be, and then normalize them to avoid, in fact, big variability in reward. So as always, we set up our hyperparameters. We have 2 important hyperparameters. The first is the number of epochs. In my case, 1000. But if you have GPU, you can use 5000. And the same thing with batch size. You can raise this to 5000 if you have GPU. So now we create a policy gradient neural network model. So as always, we take a stack of 4 frames as input. It passes it through 3 convolutional neural network, and then it's flattened. Finally pass through 2 fully connected layers and outputs a probability distribution over action. And what we can see here is that I added batch normalization, which normalizes the input of each layer using the mean and variance of the values in the current mini batch. In fact, this helps accelerate the training. And it's important that you try new strategies. It's important to be curious about that. And remember that you will not break anything. So you can experiment, add new convolutional, see if it's improved the model, change the hyperparameters, etc., etc. And if you break the architecture, you can always go back to the working implementation. Okay, so we implement as always. So we have the placeholder, so the inputs, action, and the discontinued episode rewards. So here we had this placeholder for having this variable in TensorBoard, so which is mean rewards. In fact, it's the mean rewards of the batch. So it will help us to keep track of the improvements of our model. So here we have the first convnet, the second, and the third, flatten, FC1, logits, softmax. And here we have the loss. So it's important to understand how works the loss. Remember that in the article, we explain that we want to find the weights that maximize the policy score function. The policy score function is a function that tells us how well our policy is performing. In fact, it calculates the total reward of the episode. But because we want to maximize the policy score function, we can say that the loss is a negative of the score function. Also, remember that thanks to the policy gradient theorem, we know that the gradient of our score function is this formula. So our loss will be this formula. And in fact, this formula is equivalent to that. In fact, what we must understand is that the negative of the logarithm of our policy for that state and that action is calculated here with TF and N softmax cross entropy with logits. Because here we calculate the categorical cross entropy between our action probability distribution and the action taken. If you remember the calculation of categorical cross entropy, you can see that it's the negative of logarithm of our probability distribution. Okay, so then we calculated so this negative of the log probability of our action distribution here, and we multiply it by GT, which is our cumulative discounted reward for the episode. Okay, and we calculated this using the pre-processing function here, discount and normalize rewards. And that's why we have a placeholder here, self-discounted episode reward, to send it to the neural network and use it to calculate the loss. So to summarize, so our policy loss is that calculation, and log pi is calculated thanks to the categorical cross entropy, and GT or ART is a discounted reward for that episode, which is calculated thanks to the pre-processing function discount rewards. Again, it's really important that you understand the maths behind. Okay, so here we create the graph, we initialize the session. Here we create the TensorBoard elements that we need to have a visualization of our training. So we want to keep track of the loss, but also of the reward mean. We keep track of reward mean because reward mean is important to see if our agent gets better at playing, because reward mean calculates the mean of the reward, and if this mean is increasing, it means that our agent gains more and more score, and if he gains more and more score, it means that he's better and better. Okay, so now we can train our agent, but first we must create batches. But what we must understand about batches is that the number of episodes is variant. Why? Because in the beginning of the training, our agent will be easily killed with less time step. So it means that we will have a lot of episodes. But as the training goes by, the episode will be longer because our agent will kill the enemies, so it will survive much longer. Okay? So let's understand how it works with function. So first of all, we initialize a list that will contain state, action, rewards of episode, rewards of batch, and discounting rewards. What's important about reward of batch is that we'll use also as a trick to see how many time steps we made, because at each time step we have a reward. And we use that to verify at the end of each episode if this rewards of batch is superior or batch size of not. If it's superior, it means that we must stop the creation of the batch. So here we keep track of how many episodes in our batch, and in fact it will be useful when we calculate the average reward per episode. So we launch a new episode. As always, we get a state, and we stack this state. So while true, so here what we do, we run through policy and calculate action. So we give to our neural network our states, and it will output an action distribution, so an action probability distribution. Remember that we have a situation of stochastic policy. What it means? It means that in fact, our policy will output a probability distribution over action. To simplify, let's say we have two actions, and let's say that it outputs, for instance, 70% of chance of taking action 1 and 30% of chance taking action 2. It means that sometimes it will take the action 2, and most of the time it will take action A, but it means that it will not always take action A. It's really important to understand that. So that's why here we do a random choice using the action probability distribution. It means that actions that are more probability of be taken are more probable to be taken. So we take an action, we perform the action and get the reward, and verify if the game is finished. So we store the result in our list. So states, action, rewards of episode. And if it's done, so it means the episode ends on the next state. So we put a frame of zeros, and then we stack this new frame. We append the reward of batch to reward of episode. Okay. So rewards of batch will contain, in fact, one array per episode, and in this array, this will be the episode rewards. And then we calculate the discounted rewards, okay, using discount and normalize rewards, and we append that in the discounted rewards list. And as I explained above, if the rewards of batch are superior of the batch size, we stop the mini-batch creation. Okay, then we reset the transition stores. We add an episode to the episode number. We start a new episode. And as always, we need the states and we stack the frame. Else, if it's not done, what we do, we get the next state and we stack the new next state, and our new states is the next state. Okay. And finally, what we do, when we have finished created this mini batch, we output an array of states, an array of action, an array of reward of batch, and an array of discounted reward, and finally the episode number that we will use when we calculate, for instance, the mean rewards of the batch to know how many episodes, because we will divide the total rewards divided by the number of episodes. Okay, so now we create our neural network, we initialize the weights, we need the environment, and in fact what we do at each epoch, we get batches and we optimize. So we calculate the loss and we do the gradient descent, etc., etc. So here, in fact, we must understand that all of that will be variable that we use when we want to output a lot of information, as you will see below. So first of all, while epoch is inferior of number of epoch, so we gather the training data. So we use make batch, and in fact we gather a mini batch of state, action, reward of batch, discounted rewards, number of episode, etc. Then this part is used for analytics. We calculate the total reward of the batch. We calculate the mean reward of the batch, the average reward of all training, and the maximum reward recorded. Okay, so it will use here to have much more information about how our agent is going to work. Then here we feed forward gradient and backpropagation, so we calculate the loss. And what we use to do that, in fact, we use as input the states, mini batch. Our action, we use action mini batches. And finally, for our discounted reward, discounted episode rewards. Okay, so and then we print the loss. We use that for writing TensorFlow summaries. And finally, we save the model each 10 epoch. So you can see here, for instance, so what we print the number of training episodes in that mini batch, in this case 3, the total reward, 7. So what we do, we divide 7 by 3, so we get the mean reward of that batch. Then we have the average reward of all training. And finally, we keep track of the maximum reward for a batch so far. So in this case is 7. And finally, the training loss. But we can see, for instance, here, that now the max reward for a batch so far is 15. And we can see that we have, in fact, there is variability, but we see, for instance, that the mean reward of that batch, there is an improvement of this mean reward, okay, with a lot of variability. But what's important to see is that as the training goes by, the mean reward of that batch increasing. That's why it's important to keep track of this analytic, okay? And then here we can see our agent play. So we try and we see that there is still needs a lot of training. But what we can understand is that with about 206 epoch, which is very limited amount of epoch, we still have a beginning of a rational agent. So it's really important to understand that our agent is really understanding how to play this Doom. So that's all for today. You've just implemented a policy gradient agent that is able to play Doom and killing enemies, which is fantastic. Again, remember that you can train this agent on your computer, but it will take a long time to train. My advice is to use GPU. If you don't have GPU, you can use GPU services such as Microsoft Azure or Google Cloud. Both offers credits for new users. The second advice is that you must implement the code by your own. And what I mean about that is don't just copy and paste, write it, try to understand each line, and then try to modify it. Change the architecture, change the environment, change the hyperparameters. It's really important to experiment things, because when you experiment, you learn. And second thing, you must really understand the mathematics behind policy gradients, because policy gradients is part of the new state-of-the-art algorithm, because it's a base of the new state-of-the-art algorithm. So it's really important that you understand policy gradients in terms of mathematics and in terms of implementation. I hope you liked this video. If you have some feedback, advice, or question, please write them in comments below. Next time, we'll implement an improved version of our deep Q-learning agent that learns to play Doom with another scenario where our agent must kill all the monsters in the corridor to get the vest. See you next time. So please subscribe and follow me for more deep reinforcement learning videos, and don't forget to like the video. If you like my articles and my videos, you can also support me on Patreon. See you next time, à bientôt, keep learning and stay awesome.